Hello and welcome. These are the solutions to quiz 13. So which acids are listed with their correct molecular formula? Sulfuric acid, H2S, that would be H2SO4, so that would be incorrect. Technically H2S, you could call that hydrosulfuric acid if you want to name it using the acid nomenclature system. So that would be incorrect. So we're looking for the correct ones. Perbromic acid. Perbromate would be BrO4 minus O. Perbromic acid should be HBrO4, so that would be incorrect as well. HNO2, nitrous acid, that is correct, because nitric is HNO3. So nitrate's NO3 minus, nitrite, and the us acid would be the NO2 minus derived acid. Acetic acid, this is acetic acid written out descriptively. You might see it written this way as well, but that is indeed acetic acid, so 3 and 4 are correct. So that'd be C. Which compound below has a metal cation with a +4 charge? So the key is that this is titanium oxide, so that'd be titanium 4 plus oxide because we have the 2 minus ions. So A would be right. Copper's a 2 plus, iron's a 2 plus. And we're basing this off of chlorate and nitrate being minus charged ions, hence 2 plus for both of those. And lead here also is a 2 plus minus charged ion. -2, 3 of them for -6, so that's a chromium 6 plus. So titanium is the only +4 charge in number 2. So what type of reaction could lead to the formation of yeah, I don't know why this one's on here again. But so this is like number 14 off the previous quiz. What type of reaction could lead to the formation of carbon monoxide if not conducted with oxygen, O2 present in stoichiometric excess? That's the combustion reaction. This isn't a super big deal other than pointing out the need for oxygen to be in high excess whenever we're combusting compounds. So if you have a hydrocarbon that contains CH plus O2, make sure to have enough O2 to be able to make CO2 plus water. Most reactions, if you lose one of the reactants or you run out, you just turn the reaction off. This one here is weird that will make a poisonous gas. And you have to be really careful with this reaction in the real world. So number 4, how many oxygen atoms are in a 125 milligram sample of aspirin? Okay, so the number of oxygen atoms is what we're looking for. Let's start with this in grams. 125 grams of aspirin. Let's use the molar mass of aspirin. It's actually given, that's nice, 180.15 grams per mole of aspirin. And then we know for every 1 mole of aspirin, that's 6.022 times 10 to the 23 molecules of aspirin. And then 1 aspirin molecule, so one of those molecules contains 4 O atoms. So it's like we're saying mass to moles, moles to total molecules. Each one of the molecules contains 4 atoms. So we do this arithmetic, 0.125 divided by 180.15 times 6.22 times 10 to the 23 times 4 goes to 1.67 times 10 to the 21. So it ends up being C. Analysis of an iron oxide showed that it is 72.4% iron by mass. What is its empirical formula? All right, it's kind of a tricky question in a way, but let's think about what this means. So this is using the percent mass. So remember the percent mass. We take the number of iron in the formula times the mass of iron from the periodic table, atomic weight of iron, divide by the formula weight of the thing times 100%. Okay? And so if you notice, each of these do have a differing number of iron. So the percent that's iron, we can sort of work out this way here. And so then the percent that's oxygen, we work out by the remainder. So the real question here is which of these compounds is 72.4% iron by mass. So we could just work out the percent by mass of iron in each of these and see which one works out precisely to 72.4%. We could also maybe try to be slightly more thoughtful if we could, that when we're given this is 72.4%, that maybe we could work out some bit of the ratio of irons to oxygen. Another thing we might be able to do is use this So we could work out the percent by mass of iron for all of these and see which one matches. But another approach we might do is to say, well, what if we had 72.4 grams of iron to the remainder would be our ratio, because if we know the compound 72.4% by mass of iron and the remainder is oxygen, so the oxygen mass here would be 100 minus 72.4, that's 27.6 grams of oxygen. Now we use the molar masses from the periodic table to convert to moles, so 55.85 is the molar mass of iron. So a mole of iron has this mass, and then oxygen, 1 mole of oxygen has a mass of 16.00 grams. So what we're just converting to is saying, well, each of the elements has a different molar mass. We have 72.4 grams of iron, that would correspond to 72.4 divided by 55.85. So it's about 1.296 moles of iron as a ratio in the compound to every 27.6 divided by 16 to every 1.725 moles of oxygen. Now I can divide both sides by the smallest, which is the iron. So I divide both sides by x. I keep my ratio intact. So that definitely gives me a 1 here. So there's 1 mole of iron to every, now it's going to be a fraction, but 1.725 divided by 1.296 comes out to 1.33 moles of O. So now what I want to do is take these times 2, times 3, or 4, or 5, or 6, and find the smallest multiple. 3 is going to work well. 2 doesn't quite work out, so it's going to be Fe3. And then O, 1.33 times 3, I'm pretty sure that's 4. And that does work out to 4. So that's Fe3O4. Now, like I said, you could do a double check. 3 times 55.85 divide by quantity, 55.85 times 3 plus 16 times 4, 72.4% checks out. Okay, so this maybe isn't what you expected. Like, there's a few different ways you can think through this problem and arrive hopefully at the right answer. You don't necessarily have to solve it this way. There are some other ways you might be able to solve it by thinking of the percent mass or solving the percent masses and comparing with with those listed. Moving on to number 6, what molecular formula is consistent with the findings that 1.466 grams of CO2 and 0.3 grams of water form when a 1.50 gram sample containing CHNO is completely combusted in excess oxygen? Okay, so the idea here is that this compound combusts and all the carbon is converted to CO2 and then all the hydrogen is converted to water. So every bit of the hydrogen in water comes from the hydrogen in the sample, and the O, we're just going to determine this by difference. So let's see if we can't work out for our sample the number of grams of carbon that it contains from the CO2 mass, likewise the number of grams of hydrogen from the water mass, and then the number of grams of oxygen from the sample mass, and then just minus the number of grams that's carbon minus the number of grams that's hydrogen. So the sample is either CH or O. Let's just get the O mass by simple difference. So we start with 1.466 grams of CO2, and really just want to know how much mass of that is due to the carbon. Likewise, 0.300 grams of water, how much mass of that is just due to the hydrogen? Well, for the carbon, the CO2, we could use the 44.01 grams of CO2 are present in every 1 mole of CO2, and then 1 mole of CO2 contains a mole of carbon. A mole of carbon is 12.01 grams. So we're really just multiplying the mass of CO2 by the percent mass of carbon in CO2, which would be 12.01 divided by the formula weight. You can write this out a variety of ways, but that's all that we're doing here. We're saying we'll convert grams to moles of CO2, moles of CO2 to however much mass of carbon that are present within that mole. Okay, and so we work this out, 1.466 divided by 44.01 times 12.01 gives us a mass of 0.400. So that's our carbon mass. Then we do this for water, 18.02 grams per mole of water, and a mole of water is 2.016 grams of hydrogen. So a mole of water is 18.02 grams, and then of the hydrogen, it's just about 2 grams. And so that's 0.3 times 2.016 divide by 18.02 works out to 0.0336 grams of hydrogen. Okay, now we're really not super close to solving the problem per se, other than we can get the grams of oxygen by difference by plugging in and subtracting from the sample mass. We're told we had a 1.5 gram sample, so minus 0.4 grams of that, that's carbon, minus a 0.0336 grams, that's hydrogen, leaves behind 1.066 grams, that's due to the oxygen. So now at this point here, what we can do is say, okay, we have the relative masses of the elements in the compound. Let's just convert those over to moles and then get the simplest whole number ratio. So we just got to do a gram to mole conversion. Now, sometimes it seems like you're kind of backwards doing a step you've already done, but you sort of almost need to picture this problem in two steps. Figure out how much mass came from carbon, how much mass in the sample comes from hydrogen, and then do the difference for the third element. It technically can be any third element. It's often O, but it could be N, Cl, S, really just about anything, because you're just determining that third element by simple difference. And so then we're just converting back to moles so we can get our mole ratios here. So we're doing 1.008 grams per mole of H, just using the atomic masses from the periodic table. Sometimes you wonder, well, when do you use O2's mass versus O's mass? Well, just look here. Is this O2? It says grams of oxygen, so the molar mass of just the O atom is 16 grams per mole of O. Okay, so our sample here works out to contain, in terms of, so this works out to 0.0333 moles of carbon. That's present 0.0336 divided by 1.008 works out to about the same number, 0.0333 moles of H. And then oxygen, 1.066 divide by 16 works out to this. It's nice when it works out this nicely, 0.0666, well, other than that one number, but this number of CH to O, so this empirical formula should be CHO2, and so then from there, and I'm just getting that by quickly dividing by the smallest and seeing that this is going to work out to 2. So set that to X, divide these all by 0.0333. Remember, they're all in a ratio, so we got to divide them all or multiply them all by the same number. And so this is going to go to 1 to 1 to 2. And so CHO2 is what this works out to. And so a molecular formula that's consistent with this empirical formula. So see, it says what molecular formula is consistent with these findings. Any empirical formula that has the empirical unit of C1H1O2 would be a correct answer. So A is incorrect, B is incorrect, C would be correct, D not so, and likewise for E. So we're just trying to find a molecular formula given that is consistent with this formula, this empirical formula. Okay. So we haven't quite covered this problem in class. We'll see examples in lecture, but this is your first time working through one of these examples. It's really not that hard of a problem. It's just applying the ideas of all the carbon in the sample goes to CO2, all the hydrogen goes to water. You can work out the mass of carbon that is present in that CO2 product, the mass of water present in the mass of hydrogen from the mass of water, and then likewise that third element by difference. So number 7, how much hydrogen can react with 5.5 grams of elemental carbon by the reaction below. This is getting into some stoichiometry, but I think we can handle this today. Because what we're saying here is that for every mole of carbon, it has to react with 2 moles of H2 to form CH4. And so the number of grams of H2 that can react with 5.50 grams of carbon, well, we just got to go to moles, 12.01 grams per mole of carbon. And then for every 1 mole of carbon that reacts, we can react with that 2 moles of H2. So we can react 2 moles of H2 with every 1 mole of carbon. And so how much hydrogen can react with 5.50 grams? We want to go to grams. So 1 mole of H2 has a mass, this is H2, of 2.016 grams. And so 5.5, a little less than half a mole. And so divide by 12.01. So, I did something wrong. 5.5 divided by 12.01 times 2 times 2.016. So it's about 1.85 grams. Okay, so a little less than half a mole of carbon reacts. We're going to need a little bit less than 2 moles, or a little less than 1 mole of H2, so it works out to be 1.85 grams. Number 8, we're told iron carbonate decomposes to yield the iron oxide and CO2. Consider the full balance reaction and how many moles of products form when 2 moles of iron carbonate completely decompose. Okay, so our balance reaction will look like Fe2CO3 3 solid is heated and decomposes, forms Fe2O3 plus 3CO2. Gas, solid, doesn't particularly matter so much. I don't think that you get these states right. But then our balancing is balanced because we have 2 irons, 3 plus 6 oxygens for 9, so 9 oxygens, 3 carbons. So we are in balance here. So if we have 2 moles of this compound here that fully reacts, and we're going to produce 2 moles of our product here, and then 6 moles here. So we're going to end up with a total of 8 moles. So we should have 8 moles of products form when this decomposition reaction takes place. So then we're told by a combination reaction, N2 and Ca are mixed in calcium are mixed together, resulting in the formation of Ca3N2, that's calcium nitride. How much excess reactant remains once the reaction is 100% complete? So this is looking at the case of having calcium solid plus N2 gas forms Ca3N2. So we're going to need 3 calciums, and then everything else is balanced. And so the issue here is if I initially, before the reaction, have 5.75 grams of N2, 15.50 grams of calcium, how much of them react together? Well, we could think here that one of them, or even both of them, could go to 0. Let's imagine we do this. We could say, well, how much of this needs to go with it? So if we react all the N2, how much calcium needs to react with it? I'm going to borrow some space down here to say, okay, how many grams of calcium are required to react with 5.75 grams of N2? This is kind of like the problem that we just did above, where what we're going to do is say, well, N2 would be 28.02 grams per mole of N2. Then for every 1 mole of N2, we need to react with that 3 moles of calcium. And then 1 mole of calcium has a mass of 40, I think it's 0.08. Yeah, 40.08 grams. So we've gone from grams of N2 to moles of N2, moles of N2 to moles of calcium to the mass of calcium needed. So if we do this arithmetic, 5.75 grams divide by 28.02 means we have 0.2 moles of N2 present times 3 times 40.08 means we would need 24.67 grams of calcium to react with it. Okay, so then I'm going to consume, well, wait a minute, you see the problem here? So if I go to consume, it's weird, I don't know why I can't erase this. If I go to consume or lose 24.67 grams of calcium, I don't have that much calcium. So therefore, N2 must actually be left over at the end of the reaction. We must not consume it all. So this is an impossible quantity given the amounts of calcium we have provided. So instead we need to ask the question, how many grams of N2 can react with the given calcium? So we take 15.50 grams of calcium, 40.08 grams per mole of calcium. For every 3 moles of calcium that are consumed, we can react with that 1 mole of N2, 1 mole of N2, 2 nitrogens, so that's 28.02 grams. Okay, so if we do this math, so I do 15.5, divide by 40.08, divide by 3, times 28.02, what that means is that I will consume 3.61 grams of N2 if I fully react 15.50 grams of calcium with it. And so what this means here is that we're going to lose all the calcium. It's our limiting reactant. It's the one completely consumed in the reaction. And then we're going to be left with 3.61 grams less on the N2. So 5.75 grams initially present, 3.61 grams to react. I have 2.14 grams of N2 remaining after this reaction completes. Okay, so the issue here is we need to figure out which of the reactants is limiting, which one's in excess. There's the simplest way to solve this problem is just to think your way through it. It's to say, if all of one of the reactant reacts, how much of the other one do we need to react with it? And when we calculate that quantity, if it's more than what we have given of that reactant, then we need to go switch up and do it the other way around. Like we started with consuming all the nitrogen, we found that we consumed too much calcium, and that's impossible for the given quantity of calcium. So I start with the N2 and say, well, N2 must be left over. Calcium must be the limiting reactant. It's the one that goes to 0. N2 is left over here. Okay, and so then number 10, we're asked what is the theoretical maximum yield of water if octane C8H18 completely combusts in the presence of O2. So what we have to do here is balance a reaction for O2 completely combusting to form 8CO2 plus 9H2O. And then this would require us to have a fraction of water. Somebody asked in class if we can have a fraction of water. This is a good case where we can go ahead and leave it as a fraction. So 16 plus 9 would be 25. So it would be 25 halves O2. So 16 plus 9. Oxygens is 25. 25 divided by 2 times 2 is also 25. And so the ratio here is really just thinking for every 1 mole of C8H18 that reacts, I get 9 moles of water that form. So the theoretical maximum, the theoretical maximum yield of water would be taking the mass of octane, 75.5 grams of octane, using the molar mass of octane, so 12.01 for carbon times 8 plus 18 for the hydrogens times 1.008 gives me a molar mass of 114.2. And then for every 1 mole of octane that reacts, we form 9 moles of water. And then for every 1 mole of water, that it contains 18.02 grams. Now, sig fig wise, these are perfect sig figs. Like we're counting the H atoms and things, so the mole conversions are taken to be exact quantities. We're not limiting our results here to 1 sig fig. So 75.5 divided by 114.2, that's the moles of octane, 0.661 moles. We're going to make 9 times that quantity, so we're going to make just under 6 moles of water times 18.02 grams for each one of those moles gives us a total mass of 107 grams. So we make 107 grams at maximum of water by this reaction here. Okay, so this quiz went really all the way through chapter 3. So this gets into some stoichiometry. So this gets a little bit ahead of lecture, but if you're looking at these problems, making some sense of them, we'll be seeing examples in lecture through this week's lectures and plenty more examples on future quizzes, and you're hopefully getting closer towards what you'll be seeing on next week's midterm. All right, that's all for the solution.